Okay, so now let's go into the long run production function. Okay, so in the long run, okay, like what I have mentioned earlier in this topic, okay, in the long run, we assume that all inputs are variable inputs. So that means the number of capital machineries or equipment, okay, in the short run it was fixed, but in the long run it can either increase or decrease, meaning producer can increase or decrease the number of capital in their production, as well as the number of labor. Labor is an example of variable input. So labor can also increase or decrease. So both inputs can be changed. Okay. Alright, so now let's look at the first thing that we are going to learn in the long run production function, which is Isoquant curve or Isoquant analysis. Okay, so what is an Isoquant? It represents all the possible combination of two factor inputs. Okay, the combination of two inputs, which is capital and labor, that will generate the same level of output. So this is actually this concept is actually the same with indifference curve that you learned in the previous topic. So indifference curve actually represents the combination of two products, whether product A or product B, that a producer can consume, okay, to generate the same level of satisfaction or to get the same level of satisfaction. So same concept for isoquant here. So isoquant curve represents two input, capital and labor, that a producer can use to get the same number of output in their production. Okay, so it represents all possible conditions of variable inputs that used to generate the same level of output. Okay, so let's say you are given this table. Okay, so this is the table that shows the number of capital, different number of capital. We have 1, 2, 3, 4 and 5. So that means capital can change. Okay, so capital has now become variable input. And then we have another variable input, which is labor. So the number of labor can also change from 1, 2, 3, 4 and 5. And in the figures in the table here actually shows the number of production. For example, if you are a producer and you want to produce if you want to produce 450 units of product, okay, meaning you decide you want to produce 450 and you want to know how many capital and how many labor do you need to produce 450 units of your product. So what you need to do is you just need to find the production of 450, which is here and here. So you have two combinations of capital and labor that you can use to produce 450 units of product. So untuk the first combination that you can get is here, whether you can use two capital and one labor in your production, or you can use one capital and two labors. Okay, so you jot down. To produce 450 units, you can get two combination of capital and labor. So you can either use two capital, one labor, or you can use one capital and two labor. So these two combination will generate the same level of output, which is 450. Let's say if you want to produce let's say if you want to produce 800 units of output. Okay, so you have different combination here. So you have production 800, 800 units, 800 units, 800 units. So you have four combinations of capital and labor that you can get to produce 800 units of your output. Okay, so the first combination is you can either use 5 capital and 1 labor. Okay, so that is when you want to produce 800 units. You can use 5 capital and 1 labor, or you can take the second combination here, which is 3 capital and 2 labor, or you can choose another combination which is 2 capital and 3 labor, and another combination which is 1 capital and 5 labor. So all these 4 combinations here will be if you use all these combinations, you will be able to produce 800 units of product. Okay, so when you combine all these combinations, okay, when you draw a graph later on and you combine all these combinations, you will get a curve that we call as Isoquant curve. Okay, so let's say if you draw the curve here, okay, now I'm drawing the graph to show how to construct an isoquant curve, okay, on the graph. Okay, so you have the x-axis and y-axis, so you can put capital here, labor here, or you can put capital here or labor here, doesn't matter. Okay, so dua-dua boleh. And then you do the scaling. Let's say you do 1 here, 2, 3, 4 and 5. Sama juga sini, 1, 2, 3, 4 and 5. And then you plot all the combination that you have here. 5 capital, 1 labor, 5 capital, 1 labor, which is here. And then you have 3 capital, 2 labor, which is here. 2 capital, 3 labor, 2 capital, 3 labor, somewhere here, and then 1 capital, 5 labor. So if you have graph paper, you use graph paper, okay? Alright, and then you combine all these points, all these combinations, and then you will have the isoquant curve. Okay, let's say I put it as IC 0. Okay, so this is what you get when you plot all the points here. Okay, so this will generate 800 units of product. Let's say if you want to produce more, okay, so you look at this table from the slide here. Okay, so let's say you want to produce 900. Okay, 900, so you have here, sorry, 950 lah, okay, because you have 3 combination. So 950, 950 and 950. You will have a bigger number of input used in the different combination of input that you can use in the production. Okay, so let's say you have here, okay, so you have here 5 capital and 2 labor, and then you have 3 capital, 3 labor, and 2 capital, 5 labor. Okay, so let's say 5 capital, 2 labor is here. Five capital, 2 labor, somewhere here, and then 3 capital, 3 labor, 3 capital, 3 labor, and 2 capital, 5 labor, which is here. So when you combine the dots, you will have another isoquant curve, which will generate 950 units of product. Okay, so you have different level of isoquant curve here. Alright, so when you have a lot of when you have various level of isoquant curve in one graph, you will have what we call as isoquant map. Okay, we will see that later on. Okay, so first we are going to look at the characteristics of isoquant curve. And if you look at the characteristics here, you can also notice that the characteristic is actually the same with the characteristics of indifference curve, which slopes downward from left to right, negative slope from left to right, dia slope ke bawah. It is convex to the origin, okay, it is inward, okay, towards the origin here, and then isoquant curve lying to the right represents a larger output. So the higher the indifference curve, the higher the number of output. As you can see here, from IC0 to IC1, the number of output is increasing from 800 to 950. Isoquant curve never intersect each other. So sama juga macam same as indifference curve. Okay, because using the same combination of capital and labor cannot generate different level of output. Okay, that's why they will never intersect with each other. Okay. Alright, so this is the isoquant map. Okay, so you have different level of isoquant curve. The lowest one here, okay, the down one, the bottom one here indicates the lowest level of output, which is 440 here. Okay, the second isoquant is when you want to produce 800 units. Okay, and then the top one here is when you want to produce 1200 units. So the higher the isoquant curve, the higher the production or the output that you can produce. Okay, so when you have various isoquant curve in one graph, that is what you call as isoquant map. Okay. Okay, marginal rate of technical substitution here, or MRTS here, is actually used to measure how much capital you need to reduce if you want to add more labor in your production. This is the concept of scarcity that you learned in your first topic, because scarcity means you have limited resources, which means you have to make choices whether you want to add more. In this example, whether you want to add more capital or you want to add more labor. If you want to add more capital, you have to reduce the number of labor. If you want to add more labor in your production, you have to reduce the number of capital. Okay, that is due to the reason of limited resources or scarcity. Okay, so let's say if you use this example here. Okay, so you can see that if you want to add more labor, you have to reduce a certain number of capital. So how to calculate the marginal rate of technical substitution in this case is, for example, the formula here is the change in capital, you divide with the change in labor. So if you want to add one more unit of labor, how many capital you have to reduce? So MRTS, the first one is, let's say you want to add here, okay, you want to add one more labor. So how many capital you have to reduce is the change in capital, which is 3 minus 5, you divide with 2 minus 1. So what you will get is negative 2, meaning you have to reduce 2 units of capital to add one more labor in your production. Or if you use another example here, okay, from 2, you want to add from 2 labor to 3 labor, how many capital you have to reduce is 2 minus 3 divided with 3 minus 2. So you will get negative 1. Meaning you have to reduce, if you want to add more labor in your production, you have to reduce another unit of capital. Okay, negative 1 for capital. Okay, so that is MRTS. Okay, so the last part of this topic is regarding the scale of production. Okay, so we have 3 types of scale of production here, which is increasing return to scale, constant return to scale, and decreasing return to scale. So what are the factors that will cause increasing return to scale, constant return to scale, or decreasing return to scale? Okay, so first, what do we mean by scale of production is we want to see if we increase our input, for example, we add more capital and we add more labor in our production, will that cause our output to increase more or increase just a little bit? Okay, so we want to see the effect of the changes in the scale of production. Okay, so the first one is increasing return to scale. So in this situation, okay, increasing return to scale occurs when the change in output is more than the change in input. For example, if you increase your input by 100%, let's say you add capital 100% and you add labor by 100%, your output will increase by more than 100%, let's say 200%. So you can see that your increase in output is bigger than your increase in your input. Okay, so you can actually calculate the percentage. For example, from 100 to 200, okay, the change in labor, the percentage change in labor is 200 minus 100 divide with 100 times 100, so you get 100%. The change in output here, you can see from isoquant, the first isoquant to the second isoquant, from 20 units to 60 units. So the change in output is from 60 minus 20 divide with 20 times 100. So you will get 200%. That is how you calculate the percentage. Okay, change in the input and output. Okay. Alright, and then we are going to look at the second scale of production, which is constant return to scale. Okay, or the first one here, increasing return to scale. How can it happen? When you increase just a little bit of input, you can get more output. The reason is because your production is efficient, meaning your laborers are specialized in their own job. Let's say if you produce cars, for example, a certain group of labor is focusing on assembling the engines. A certain group of labor will focus on assembling the body, and then another group will focus on painting and so on. So they are specialized in their own tasks. So that will be, the production will be very efficient, or you use better technology in your production. So that's why when you add more input, you will gain a higher number of output. Okay, now let's continue back to constant return to scale. Okay, constant return to scale is a situation where the change in output is the same with the change in input. So adding, for example, 100% of input, you add additional 100% of input, for example, labor and capital, you will get the same increase in the output, which is also 100%. So the change in input and the change in output is the same. Okay, and then the last one is decreasing return to scale. So this is a situation where the change in output is lesser than the change in input. Okay, so when you add, let's say, 100% in your input, okay, you add 100% of capital and another 100% of labor, your increase in output will be lesser than 100%. Output will increase, but only by 50%. For example, from 20 units, okay, as you can see here, from 20 units to 30 units. So that is 50% increase. So you can see the change in output is lesser than the change in input. So what are the reasons? Is because of this economies of scale. For increasing return to scale, this is due to economies of scale. An example of economies of scale is specialization lah, yang the one that I mentioned just now. Okay, and then for decreasing return to scale, that is due to these economies of scale. For example, mismanagement of labor, mismanagement of capital, and so on. So we are going to look at economies of scale and these economies of scale in detail in the next topic. So this is all for topic 5.